we have the CPU, right? And then we have commands being sent to the GPU, and the way you send commands to the GPU, right, is vertices, right? Vertex these. Really should have made this canvas larger, but I did not, so. Oh, there we go, that's easy to read. Now, the important thing to note here is that, there, a vertex or vertices is not just a point in space. We have multiple things that it can be. So we do position, 2D or 3D, color, can contain UVs or sampler, texture, coordinates. It can contain more colors, right? In the beginning, it was position, color, and UV, and those were fixed. This was the fixed function pipeline. When they introduced shaders for real, they created ways to allow you to describe which attributes would go with each vertex, or which attributes were given to a vertex, and then say, here's the data for this attribute, or like interleave them. There's a bunch of different ways to do it, but the main point is that when you are submitting draw requests to the GPU, this is what you're sending. Right? Back. Come on. There we go. You are sending multiple vertices. Each vertex contains usually position, sometimes color, often texture coordinates, and then any additional attributes that differ on a per vertex basis. So that includes things like if you want to have the GPU do like a flag waving effect, you might include weights, and then have the GPU do some calculations with those weights, right? If you want to do multiple textures in one draw call, you might include in your vertex which texture to read from. Does that make sense? In very, very practical terms, what you are sending, since you've done C and some C#, I think this will make sense. In very, very practical, real terms, what you send to the GPU is an array of, let's say you're doing 3D or 2D, right? You send an array, a contiguous array in memory, like a malloc or calloc or whatever, malloc or a C#, new array, whatever, of float values. Right, so if you have 100 items, you would send 200 floats for the positions, X and Y. You would send 100 4-byte color values. Or, if you're providing the colors as floats, you would send 400 floats in a different buffer. You can send 200 U and V texture coordinates, right? So each of these, there are ways to kind of merge them into one buffer, but generally the best way to think about this is you have basically a malloc array for the position. You fill in the position for each vertex in sequence, and you send that as one giant blob of data to the graphics card. You do the same for color, you do the same for UVs, you do the same for any other vertexes that you want to tell the GPU to process. Now, a vertex is a point in space. It is not a shape. So the next step is I'm gonna step 1. Cool. Step 2 is CPU, GPU, actually, hey, ASCII art. Step 2 is we're going to send to the GPU a set of indexes, which is an integer into the vertex array. That's it. And, well, mostly it. So usually this is going to be unconnected triangles. Usually this is going to be unconnected triangles. So a perfect example that you'll see quite often is if I want to draw a box. Ta-da-da-da, box. So I submit vertices 1, 2, 3, 4. And now, if draw a line here, yeah, that's good. My text tool. Now, if you see, if I draw 1, 2, and 3, I get a triangle. If I draw 3, 2, 4, I get another triangle. By doing this, I've given 4 vertices, which contain most of the data, and then I give you 6 indexes, and we have a triangle, or we have a square, a quad, rectangle, sorry, not square. We have a quad. Let's say, though, we have a maybe more complicated example, which I cannot easily draw here, but we'll do our best. Boop. Yeah, this will work. Something like this. That's a terrible octagon, but you get the idea. Yes. Yes. Indexes connect sets of vertices into triangles. There are other draw modes. There are quad draw modes, so you can say 4 indexes equals 1 quadrilateral. And it's called quads because a quadrilateral could be boop, 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 boop. That's a valid quad. Right? And if you're looking at that, you might go, oh wait, that kind of looks like it's facing like this way. It could be. But generally, usually most of the time, you do triangles. Why? Because yes, assuming all the verts of the quad are coplanar. And that's kind of the issue, is, while quadrilaterals are great, turns out that it's a lot easier to make complex high polygon meshes out of triangles than it is out of quadrilaterals. That's really what it boils down to, right? Because I can make this guy, I can make this poorly drawn octagon into a bunch of triangles, right? But I can't really make it into a bunch of quadrilaterals nearly as easily. Basically, there's a lot of research done into how to turn polygons into a bunch of triangles. We're really, really good at that. We've done a lot of very smart people have done a lot of math to figure out how to do that easy peasy. And so that's what we do. Also, in reference to your coplanar point, yeah, they would have to be coplanar. I think that's another piece of it, is that the 3 points of a triangle will always be coplanar for some plane. by definition, or by construction, essentially, you cannot have a triangle. You can't have 3 points in a 3D space that are non-coplanar, which I'm pretty sure makes some of the math easier. Anyways, so now we've gone step 1, we're sending a bunch of vertices to the GPU. Yeah, you changed the plane, but who cares? I mean, we're changing things planes all the time, right? Every time a 3D mesh moves around, you're changing the plane. And by the way, the plane is often referred to as the normal. Basically, one side of a triangle, if you have a mesh, right? If you have, imagine a rectangular prism, a cube, right? For each triangle that makes up that cube, one side of the triangle is going to be the outside, the other side is going to be the inside. The outside, the vector, the three-dimensional vector pointing, quote, outside, for each given triangle is called that triangle's normal. You may see references to normal mapping. That is, the best way I can describe it is shading, right? If I take this nice gray here, and I do this, right? I kind of, that's good enough, right? And I make that kind of gray, make this kind of gray. Then, if I say adjust, like by default the normal is going to come straight out of the screen, but adjust it by like the color a bit in some certain way, right? Then you can make a flat plane appear as if it's curved using normal mapping. Anyway, we'll continue on. That's a more advanced topic, and to be honest, I am not as familiar with normal mapping and three-dimensional rendering. I am much more familiar with the two-dimensional rendering aspect. So, let's move on. New frame, new cell, new frame who dis. So, step 3. We've drawn, so in step 2, we again sent indexes. Oh, it's fine. That's fine. I should pause this though. I'll cut off like 20 minutes or so off of that, maybe 30. I'll figure it out later. It's fine. Part of the point of streaming for me is to educate, and I can do this stuff by myself. I don't really need I don't need an audience to write code. But educating is something that I love doing and really can only do with other people. So anyway, step 3. So we've sent the indexes, we sent the vertices. We've sent the indexes that we want to use. Final thing I wanted to point out here is if I'm marking these indexes, right? 4, 5, 6, 7, 8, and so if I'm marking these indexes, right, if the center point is 0, my triangles are going to be 0, 1, 2, 0, 2, 3, 0, 3, 4, 0, 4, 5, 0, 5, 6, 0, 6, 7, 0, 7, 8, and 0, 8, 1. Right? The important piece of indexes is that you can reuse indexes to reference the same vertex multiple times. That's basically why indexing exists, because the vertexes are... A vertex contains a lot of data, right? It contains... You've got 2 or 3D positions, you've got colors, you've got all sorts of stuff. And an index is a 4-byte integer. So you can send all the vertexes or vertices that you need, and then, yes, got it. The reuse of an index is how you know 2 vertices will be, or 2 triangles will be touching in some manner if you're reusing one index. 2 triangles will share a side if you're reusing 2 of those indexes. As for something like a circle is just going to be an octagon, except what if we made it like 40 sides? That's it. What if we made it like 40 sides? And then, basically, each individual side is small enough that you don't notice that it's not... that it's just a very high... It's just a polygon, a regular polygon with a very large number of sides. That's how we render circles. It's all just a trick. If you're rendering them relatively small, like this size, about 30 is a good number. If your circle is going to take up your entire screen, you probably want something closer to like 60. If you have more than 60, why? Why? Especially because if you think about a full circle is 360 degrees, so if you have 60 individual flat surfaces, right? If you have a 60-sided polygon as your circle, each flat surface is 6 degrees. It's nothing. That's nearly imperceptible unless you blow it up, unless you're drawing one circle on a 4K monitor. Maybe bump it up again to like, I don't know, 80? 90? Yeah. Anyway, that is circles. We don't draw circles. We draw a bunch of triangles. We don't draw squares. We draw a bunch of triangles. Now, step 3. So I'm actually going to go back here. Actually, no, I'm not. I'm going to finish out thing here. Wow. So GP GPU. Let me just make this actually fit on the screen. So, we've established that, let's go back to our example here of a square. I'm gonna just do that. Go here, paste. Move this up a tad. Okay. So we have two triangles, right? Two triangles. And so 4 vertices, 2 triangles, 6 indexes. Right. The first thing that we hit is the vertex shader. So the vertex shader takes each individual vertex that it is given and transforms it. Now I want to be clear, it does not transform it in context. Usually. There's a little bit going on there, but it's transforming each vertex individually. I mean, it is transforming it in, no. Yes and no. Point is, transforming each vertex. Generally, it is... I think there may be some extensions where you can like get where you could access information about subsequent or previous indexes. Yes, that is generally the goal. All the vertex shader knows is the specific vertex it's chewing on. There may be some extensions for like specific GPUs and specific APIs for those GPUs that let you get external data, but generally you don't want to, because that's going to slow things down. Really what you want is a shader, say vertex shader, that's just going to do whatever it is that one vertex. Yeah. And we do that because, again, if I'm drawing a big circle with a 30-sided polygon, there's not a really good reason to process that center vertex 30 times when I could just process it once. Right? So why do extra work if you don't have to? So that's the vertex shader. The fragment shader, I'm actually gonna... Fragment shader, I'm gonna do in green, and back. I got like spray paint here. The fragment shader does each pixel. Each individual pixel gets its own fragment shader. And the output of the fragment shader is the actual color that goes onto that pixel. Mostly. Mostly. I'll add a step. I'll add a step here. Hold on. This is one that I think a lot of people forget about, but is important. So, when you're rendering in any of these things, you're not really rendering to a screen pixel. You are rendering to another texture. This used to be called there's different terms for it. Frame buffers, render to texture. These are the same thing. These are literally the same thing. A frame buffer is just a texture that the GPU will write to. That's it. That, like, I mean, yeah. So it's the texture that the GPU is going, oh, okay, the output of your shaders is going into this texture, and then I can use it for more operations. There is a texture, or a render texture, or a frame buffer. I'm going to use the term frame buffer. That's just what I'm more familiar with. There is a frame buffer that whenever the screen requests a new frame, the GPU goes, here's the current contents of the frame buffer. And that is how pixels get to the screen. The screen says, hey GPU, I need a new frame. I'm ready to refresh, give me a frame. And the GPU says, here's the contents of the current frame buffer. Yes. If you've heard of like Vsync, that kind of thing, basically the trick there is intentionally causing Vsync, like screen tearing issues, more or less, to achieve effects. It's actually the same reason why emulators tend not to... The colors, if you run, especially like SNES games, on an emulator or on a modern monitor, they tend not to look as bright. And they tend to be kind of washed out or muted colored because the games were literally designed to run on a CRT. And a CRT stands for cathode ray tube, literally beaming light directly into your retinas. the reason that CRTs are so heavy is because they had to have they had to have lead shielding to protect users from radiation. Well, yes, but the point is the same, that the amount of light produced and the kind of offset light, not offset, basically the light bleeding over from one pixel onto another meant that while the RGB values might be more muted, the actual way that they appeared on screen was different, right? And you can achieve the same, not the same, but similar changes if you just go into your monitor settings and turn up the contrast or turn down the contrast, right? Point is that the physical presentation of pixels is distinct from their RGB values in the GPU. The way that usually works is that your screen requests basically the next frame of pixels from the GPU, and the GPU says, here is the back buffer, or here's the current buffer. Here's the current buffer. Whenever you render a frame, you are rendering to a back buffer, and then swapping the back buffer and the buffer that the GPU is sending. Yes, exactly. You got it. And so that's actually why Vsync issues occur. Because it's not swapping the buffer data. It's literally a pointer swap. The GPU is doing a pointer swap and going, okay, we're pointing to this buffer instead. And so if you do that pointer swap halfway through rendering a frame, well, suddenly, the top half of your screen is one frame and the bottom half of your screen is a different frame. So that is what screen tearing is. That is why Vsync exists. That's why variable refresh rate exists. All of that kind of stuff is because that's how GPUs send data to the screen, and it's real annoying to people when they just see this brief flicker of weirdness. Anyway, Vertex, to conclude, yeah, it's annoying to everybody, so that's why those technologies exist. Now, you might kind of be wondering, what exactly does a Vertex shader do? Because it kind of seems obvious. Like, if I've got, my vertexes here, 1, 2, 3, 4, what is this actually doing for me? Yes. Yes, a fragment is a pixel. A fragment is a pixel on the output buffer's texture. It has no direct relation to the number of pixels on the display. You can... Lust! Hello! This is not a door. This is me explaining how GPUs render images. Yeah. We're talking tech. Yes, and that is why it's so easy to change game's resolution, because the GPU literally is going, oh, my back texture, yes, you change the size of the buffer texture and scale it. That's it. That's it. Same thing. It's the same process that happens if you're trying to render a 32 by 32 pixel sprite as 64 by 64 or as 16 by 16. Same work going on. And it is just the GPU basically rendering from one texture to another. Oh, what I was going to say is, you can absolutely render to, you can like make a texture that's just 128 by 128 and then draw into that texture. Like, let's say I have yeah. Yeah, sorry, Lust. You came in expecting doors, and you got deeply technical discussion on the inner workings of graphics cards.